students, and welcome to another lecture for Natural Language Processing. The content and slides for today's lecture come from our textbook Speech and Language Processing, which you can find here. This is the third lecture that I will be recording for this class, but again, you're welcome to watch these in any order that makes the material meaningful and useful for you. So today we are talking about string similarity, right? How do I look at two words and say how close they are to one another, how similar or dissimilar they are to one another? Some applications of this would be, for instance, spell correction, right? Let's imagine we're scanning a document and we see that a user has typed graffe. Well, there are several correct words that are similar to graffe, which is not a word in the English language, right? So we would need to select from this short list of 4 possible correct words, which is the most similar, right? What is most likely what the user intended to type, right? Or we might be talking about computational biology, where we might want to compare 2 strings of nucleotides and say, where are they similar? Where do they overlap, right? What alignment of these 2 strings gives us the greatest similarity between the two, right? So this has applications in machine translation and information extraction and speech recognition, right? And so today we're going to be discussing a method for computing string similarity called edit distance, and specifically the minimum edit distance, right? Which really means, how can I look at 2 strings and perform simple operations to transform one string into the other, right? And so these simple operations, the 3 that we'll be using, are insertion, right? So adding a character to one string, deletion, removing a character from one string, and substituting, swapping out one character for another. Right? And so by applying these 3 simple operations, the idea is that we can start at one string, end at another, and by counting the fewest number of operations that I can apply to get from one to the other, I will have computed the minimum edit distance, right? And our conjecture for today is that this will tell us how similar 2 strings are to one another, right? So let's think about the distance between intention and execution, right? And a first step we might want to take is aligning the 2 of them, right? Finding exactly which characters overlap between the 2, right? For 2 reasons. One, because this gives us kind of an ad hoc approximation of how similar the 2 strings are, right? If I can find a good alignment between the 2, I have found a measure of similarity, right? And 2, for computing our minimum edit distance, this is how we're going to avoid unnecessary operations, right? So notice with the second E in intention, right? I can align that with an E in execution, so I don't need to perform an operation on that. With this T and I and O and N, I can align all of those, so I don't need to perform any operation between the 2 of those, right? And so once I've got my alignment correct, right? Well, then it's pretty easy to see. Okay, cool. I just delete the I. I can substitute an E in the place of that N. I can substitute an X in the place of that T. The E is fine, right? I'll insert a C. I'll substitute a U in the place of the N, and then T, I, O, N are fine. So I've done 1, 2, 3, 4, 5 operations, a deletion, an insertion, and 3 substitutions. So if we think of all operations as being equally costly, then I have done 5 operations. But really, if we think about what a substitution actually is, a substitution is actually 1 deletion and 1 insertion. So we might want to charge a little bit more for that, right? We might want to say, no, actually, a substitution is a cost of 2, since it's really 2 operations that we're just calling one. Either one will give you an accurate estimation of minimum edit distance as long as you're consistent. For today's coding exercise, we're going to be using a cost of 2 for a substitution. And just to see that this has applications outside of just natural language processing, right? Here's an example of finding an alignment between 2 genetic sequences, right? So this same tool has applications outside of just the focus of this class. And here we can see conceptually that this can be applied at a token level, at a word level, right, above just the character level, right? So here we can use minimum edit distance to evaluate how similar two potential translations of the same sentences are. Okay, cool. So now I think we have a pretty strong understanding of what minimum edit distance actually means. So let's start working towards calculating this number, right? How do we actually find a minimum edit distance? And if we think far, far back to our intro to AI class, we learned that we can state any problem as a search space, right? And so finding a solution to that problem is really about finding the minimum distance between 2 nodes in a graph defined by our problem space, right? So if we think about it in those terms, well, then we've got some initial state, which is one of our words. We have transitions between states. Here are our operators, which are insertion and deletion and substitution, right? We know our goal, where we're trying to go, is the other word that we're converting to. And our path cost is just going to be a weighted step count, right? And I say weighted here because we're running with the idea that substitution is a little bit more expensive, right? So now from our initial state, our starting node here, intention, well, we could apply deletion to the I, and that gets us to a new node. Or I could apply insertion of the letter E at the start of this word, and that gets me to a new node in my search space, right? Or I could apply substitution, I for E, and that gets me to a new node in my search space, right? And so now, stepping and stepping and stepping along nodes, I just need to count the cost of my path, and I will have solved this problem of minimum edit distance. But if you stop and take a minute to think about the size of that search space, right? We visualized it, just a tiny slice of it here, right? Applying each of 3 possible operations, each at one possible position, but actually I could delete the I or the N or the T or the E or the N or the, okay, and so on and so on. Okay, I can insert before the I, before the N, before the T, before the E, before the N, before the T, and I can insert any one of 26 possible letters. Okay, and I can substitute at any one of these letters, and I can substitute it for any one of those possible letters in the English alphabet. So if we think about the branching factor of this space, right, from any node, how many steps do I have out to different nodes? That's an enormous branching factor, right? And the total search space is enormous. And troublingly, we should see that we have infinitely long search paths, right? I can insert the letter A before this I. And then before that letter A, I can insert a letter A. And then before that letter A, I can insert a letter A. And then before that letter A, I can insert a letter A. So a naive search algorithm could potentially follow an infinitely long search path, and even a very well-optimized search algorithm is going to have to deal with a very large search space, right? And we might also find many paths from one node to the other, but we only need the shortest of them, right? So we might have to calculate many different paths, each at great cost, and from them find the shortest of all of them. So thinking of this as a search space problem can potentially be very expensive. So let's back up and let's approach this from a new direction, right? Let's just think of the function we're trying to define, right? I want to find the edit distance between two strings x and y, but let's think about what the edit distance of substrings from each of those would be, right? Let's define a new function here, the distance from I to j, or the distance given I and j, right? Well, let's just say, okay, that's going to be the edit distance of this string x up to character I, and this string y up to character j, right? And so I can start with low values of I and low values of j and work my way up to where I'm computing dnm will now be the minimum edit distance of x to y, right? Since x from I to n is all of x, y from 1 to m is all of y, and apologies for the computer scientists in the audience. Our authors are using a 1 indexed character array here to represent a string. But dnm will now be our total minimum edit distance. So if we just had some way to express dnm in terms of substrings of smaller versions of x and y, slices of x and y, well, then we could sneak up on a solution to the minimum edit distance between x and y. So let's figure out how to do that. And we're going to do this by applying dynamic programming, right? Dynamic programming is the process by which we solve large problems in terms of solutions to simpler versions of the same problem, right? So we're going to take a bottom-up approach. We're going to use our dij function, starting with small values of I and building up until we get to the edit distance between two complete strings. All right, so here we are. We're going to use Levenstein's definition of a recurrent function that defines this dij that we are talking about, right? And this is also going to give us a bit stronger intuition as to why that substitution becomes a to-cost operation. So now let's initialize some base cases for our recurrent definition of the dij function, right? And so let's think about what di0 would be, right? So di means all of the characters from that string x up to some point I. 0 would be no characters from that string y. So di0 is the distance between some substring from x and the empty string. And intuitively, I think we could see that the edit distance between any substring and an empty string is just deleting every character from that substring, right? So the distance di0 must just be I. The minimum number of operations I can do is deleting I characters. Similarly, the distance 0j just means deleting j characters, right? So the distance 0j is j. Cool, so now I have two base cases, right? And once I have two base cases, or once I have some base cases, I can start defining a recurrent function based on my understanding of those base cases, right? So for dij, I can define the distance as being the minimum of three possible options, right? Either one smaller substring from x plus 1, right? One smaller substring from X with an extra insertion. One smaller substring from Y with an extra deletion. Or here is a function or here is the row of this function representing a substitution, d I minus 1, j minus 1, right? So a smaller string from X and Y plus the cost of a substitution. Well, if the characters are not the same, that substitution costs me 2, right? Because we're using Levenstein's definition. If those characters are the same character, if x of I is equal to y of j, then that substitution costs me nothing, right? So distance of I of j is just the smallest that I can get from these possible values, an insertion, or one deletion, or one substitution, which might cost me 2 or might cost me 0. And here we are with the two strings we were looking at initially, right? We're finding the distance between intention and execution. And we've sort of filled in a table here the base cases, right? So here we've got a table representing all of the characters of intention filled in rows here, all of the characters of execution filled in columns here, with an extra character inserted here representing a null string, kind of the start of each string, right? And we filled in our base cases, right? So the distance between an empty string and an empty string is 0. The distance between an empty string and the letter E is 1, right? 1 insertion. The distance between an empty string and the characters EX is 2, right? 2 insertions, right? Or following up the column here, the distance between I and an empty string is 1 deletion, 1, right? The distance between IN and an empty string is 2 deletions. Cool. So our goal now is to fill in the missing cells. And we've got the tool that we need to fill in those missing cells because we have a function that will give us the value of any cell as long as we've already filled in d I minus 1 of j. Well, that's just one step to the left in the table. d I j minus 1. Well, that's just one step down in the table. d I minus 1 j minus 1. Well, that's just one step diagonally down and to the left. And I see that here, for this cell indicated by the red arrow, yes, I have all of the necessary information. So I can fill in a value using my formula, right? One step to the left plus 1. One step down plus 1. One step down and left plus 2 if they're different and 0 if they're same. Well, let's fill in some values for that. A step to the left plus 1 is 1 plus 1, so that would be 2. A step down plus 1 would be 1 plus 1, well, that's 2. A step down left plus 2, because I and E are not the same character, so 0 plus 2 is 2. So I just have to pick the minimum of 3 values, 2, 2, and 2. So we would fill in this row, or this cell, sorry, with a 2. The distance between I and E, right, the substring I by itself and the substring E by itself is 2. 1 substitution. So go ahead and, if you're so inclined, pause the video here for a second and try working through this for a few iterations. Right? Try filling in some of our missing cell values, right? So you'll see that as you fill in IE, well, now we have all of the required information to get the distance between I and EX, or IN and E, right? And then fill in and fill in and fill in. And our goal is to fill in this top right cell. Right? If we process through this entire table, we'll get one value in the top right, and that value is going to give us the minimum edit distance between intention and execution. And this is what that looks like, right? I don't know if you filled in this whole table yourself. Maybe you did. Maybe your patience is substantial and impressive. Or maybe you just did a few cells to kind of get the flavor of it. But this is what the table filled out looks like, right? The difference between I and E we already found was 2, right? And then, so going from there, the distance between IN and E is 3. And we'll notice here that our authors have sort of highlighted for us the minimum value in each row, because we'll notice that it's not consistent, right? If I start from our top right and walk a couple spaces left, I get a larger minimum edit distance. And if I walk a couple spaces down, I get a larger minimum edit distance, right? And what's going on there? That's the effect of alignment, right? You would think that deleting characters from intention or execution would always make your minimum edit distance cheaper. But that's not the case, right? Since intention and execution have so many characters that align so well, right? One of the E's and the TION, those are essentially free operations, right? So by following this sort of critical path from the bottom left up to the top right, these blue characters that our authors have highlighted for us, that shows the points of maximum possible alignment between the substrings as we build them up. So here, for instance, this value 5 between INT and EX, right? This value 5 between INTE and EXE, right? Show our points of maximum possible alignment. Up to an 8 in the top right is the minimum number of operations we could do to turn intention into execution. I hope that this has made some sense to you. I hope that you have some basic understanding of the fundamentals of minimum edit distance. But to help solidify our understanding of this concept, we are going to jump over to a notebook in my Google Colab, and we're going to code this out. So I will see you in 1 second for our coding exercise for this lecture. Alrighty, welcome back. I have got us here my coding environment of choice, which just happens to be a notebook. I've gone ahead and sketched in a few cells for us, right? I've got our challenge for today is going to be finding the minimum edit distance between goat and cat, right? And I think if we look at this, right, take a moment to draw this out yourself. Take a moment to try to find the minimum edit distance on your own. But I see A and T align. So if I delete G and then substitute O and C, I've gone from goat to cat. I've done a deletion and a substitution, right? Deletions cost me 1, substitutions cost me 2, so my minimum cost here is 3. Right, so just keep that in mind. This will be our test case, right? We'll be able to assess our implementation. I've gone ahead and imported NumPy already, since I know we're going to want to build a table similar to this. I've gone ahead and pulled up some of my documentation for NumPy. I always like to have my documentation easily at hand while I'm working. And let's start thinking about what we're going to need, right? We're going to need a table with a number of rows here equal to the characters in our first string plus 1, right? Since we've got these empty string row and this empty string column filled in. Okay. And likewise, I need a number of columns equal to the number of characters in my second string plus 1. So I can go ahead and do that. Yeah, okay. So my distance matrix is going to be equal to, I'm going to use the np.ones function to give me an indie array with some default values filled in, ones in this case. And so the size of this array I'm passing in as a tuple that's going to be the length of string w1 plus 1, right, since we need that extra row and that extra column for my empty strings, and then the length of w2 plus 1. And now let's think about what's going to happen if I fill in default values of 1, right? Since we're sort of working through and filling in values using the values of adjacent cells, if I fill in a default value that's very small, right, that might pass in bad information. Right? Granted, if we work in an orderly fashion, we will only be referencing cells for which we have filled in a value, but I want to prevent that from ever happening. If I read a value from an unfilled cell, I want its value to be very, very high. So I'm going to go in and fill in infinite. There we go. I will eventually find the F on my keyboard. Cool. I'm going to go in and fill in an infinite value for all of the cells in my distance matrix. Let's go ahead and take a peek at that just to make sure I haven't goofed anything just yet. And here we go. Okay, so I've got an indie array, all full of infinites. The number of rows here, I can see GOAT plus 1. The number of columns, I see CAT plus 1. Cool. I think we are ready to get started. All right, so let's fill in our default values, right? Our I0 and 0j values. So for I in range, let's see, len w1 plus 1, I can say that distance mat of I0 is equal to I. And let's give that a run. Okay, cool. So now something we're going to notice right away is that for convenience sake, in the slides, our authors worked from bottom left up to top right. For convenience sake, to make the coding a little easier, I'm actually going to work from top left down to bottom right. So this cell on the bottom right will eventually be our correct answer. So take a moment to do some transforms and some flipping in your brain. All right, cool. So now we also need to fill in the default values that we know in the columns. And I'm using single character variable names. Yes, that's often a very bad practice. I'm trying to keep as much consistency with the sort of nomenclature of the slides as possible. And we'll see if that gets me into huge trouble. Ooh, we don't want to do that. No, thank you. There we go. J is equal to J. Okay. I think we've done a pretty good job of filling in our default values. So now we just need to iterate kind of through every position, filling in when we know that we can, right? And we need to use this function to fill in the values for the missing cells, right? So one step left plus 1, or one step down plus 1, or one step diagonally plus either 2 or 0, depending on if the characters match or not. So let's fill in this function, right? And we can see here, I've already got myself an empty function definition just to start filling this in. We can be good Python programmers and announce to the world, hey, this is going to be mp.index nd array. Right? I like to use type hints as much as possible. They are not mandatory in Python. They are just a very good and helpful thing. This is an integer. S1 is going to be a string. We're only passing in a character at a time. Notice, right, this is only a comparison between one character and one character. Python doesn't think character is a data type, so we're going to pass in a string. Okay, and the return of this whole thing, let's see, what do we get back? Right, it's either this distance plus 1, this distance plus 1, this distance plus 2. Those all look like integers to me, so let's say this gives back an integer. Cool, right? And now we've done our due diligence as Python programmers. We have announced our data types to the world, even though that is not mandatory. So now we need to calculate those 3 distances. All right? It's either one step to the left, I minus 1, comma j, plus 1. All right, so let's just go ahead and save that. I'll call it D1. Okay, or it's one step down, which is, let's see, I of j minus 1 plus 1. Or here, D3 is going to be one step diagonally. So this is D of I minus 1, j minus 1. This is plus 2 if S1 does not match S2. Otherwise, it is just this value by itself. I am using the dreaded inline if-else, right? This is just Python's version of C++'s ternary if-else operator. I like it. You might hate it. I hope that you're writing some code yourself as you're watching this video. If you prefer to use an if-else stretched out over a couple of lines, totally fine. Not going to affect the runtime of your program. Cool. So now we need to find the smallest of these 3. So we can just return the minimum of a list containing those 3 values, D1, D2, D3. Cool. All right. So now we need to iterate over. Well, let's see. How can we iterate? Right? Once I fill in this value, then I can fill in this value or this value. Right? And once I fill in this value, I can fill in this value, but not necessarily this value if I don't have this value. So it looks like it is safe to iterate across a row, right? Once I have this, I can get this. Once I have this, I can get this, right? Now I've got values for all of these, which means it's safe to get this. Once I have that, it's safe to get this. Awesome. I'm just going to go across the row, across the row, across the row, and then across the row. So let's go for row in. Now this is allowable syntax in Python. I'm going to say this is not a best practice, right? Actually, you know what? If I'm saying it's not a best practice, why don't I just do the thing that is the best practice, right? For row, comma, cell. Here we go. Sorry. For, yes, row, comma. What? Nothing in enumerate. D distance matrix. Okay, so this is going to give me back one row at a time. I actually do need the values of that row, so I'll get row vals. Unfortunately, we're updating row vals as we go, so I want to ignore that. I'm not going to use that. right, for column, comma, let's see, schmoot, and enumerate distance mat of row. There we go. We're going to see if this causes an absolute train wreck. I've tested this with the hated range len permissible but disliked Python syntax. I'm going to try to clean it up. I'm going to try to do it the right way for y'all. If this is a total train wreck, we'll go back to the hated syntax. Okay, now distance mat of row comma column is equal to, we're just going to use our function dij. And now what does dij need to get? It needs the I value, which is row. It needs the j value, which is column. It needs, and this is one of the nice things about using those type hints, right, is that now we're getting our good suggestions here. We need the value of the character at I, which is w1 of row. We need the value of the character y of j, right, which is w2 of column. And that's about it. So I think we are ready to give our code a quick test. And of course, we get an error because I didn't read my own hints, and we need to pass the matrix itself. There we go. Now, of course, this is Python. Distance matrix is applied at global scope, right? Just for kind of cleanliness, right? Rather than referencing a global variable, I'm passing in the matrix, which I think is a better practice. But now that we've done that, let's give this a run. And of course, let's see, row column is going to go one step out of bounds for those strings. So let's downshift those. And let's see, let's think about what's just happened, right? We got back a matrix full of nans. Row is going to start at position 0. So we've written a pair of nested loops here that are going to start filling in values here, but we want to start here. We want to start with row and column values equal to 1, not 0. Give me just a second. I'm going to rewrite this in the hated range len syntax. I'll be back with you in just a second. All right, so just a quick swap back into range. Now I can define my range as starting at 1, which is handy. We still need to run one extra character in each direction. And if we run this cell now, we see here in the bottom right is our 3. So we can go ahead, let's see, use ourselves a nice format string to get our output. There we go. We need to terminate that string. So now the distance between the two is all the way at the end, all the way at the end. And there we go. We have our program correctly outputting the distance between goat and cat is 3, right? The cost of 1 deletion and 1 substitution. And just for giggles, let us try the original words, intention and execution, right? Let's apply one more test case, and we know that the distance between the two should be 8. This is the part where I probably misspell either intention or execution. And we get that the distance between the two is 8. So, boom, there we are. Just like that, in a few lines of Python, we have used dynamic programming to implement minimum edit distance between two strings. So, thank you very much for your attention. I hope that this video has been helpful and informative for you. And I will see you all back in class or in our next video.